All right, so it is 3:30. We can go ahead and get started. Let me just move this out of the way. All right, cool. Let's see, what do we got up? So I did post our homework assignment 2 on Canvas on Friday. So as with all of our homework assignments, that will be due this Friday. And as always, if you have any questions, we've got Jordan's office hours on Wednesday. We got my office hours on Friday. Yeah, and if you have any other questions in the interim, feel free to post those on Piazza. But yeah, basically, homework assignment 2 is going to be all about Unit 2, in which we were discussing the myriad of different ways in which we might go about essentially defining a cluster. And again, each of these different cluster definitions can, they essentially help inform all of the myriad of different clustering algorithms that exist that, some of which are going to be more effective than others when it comes to identifying the particular clusters that might exist in a data set that we can see with our eyes. So for instance, what we can see with our eyes are 3 clusters in this data set here. And we'd like to determine which of the 4 cluster definitions that we discussed on Thursday is going to be the most suitable definition that we can essentially incorporate into a clustering algorithm that's, attempting to find clusters that are, similar to each other, basically sets of observations that are similar to each other, put them in the same cluster, and then find clusters in which the observations in different clusters are what we would consider dissimilar to each other. So try to submit in the next few seconds. But again, you want to think about our goal is to identify these 3 clusters here that we can see with our eyes. So well-separated, density-based cluster, graph-based cluster, or a prototype-based cluster. Okay. So let's see here. So I'm seeing a high proportion of people said the well-separated definition of a cluster is going to help us identify these 3 clusters here. So actually, what we're going to see is that, for instance, so the blue cluster and the red cluster, we might say are well separated from each other. And again, we want to think about, what does it mean for 2 clusters to be well separated from each other? Well, there's a lot of, ways that we could answer that question. But, when it comes to identifying or basically separating these 3 sets of points from each other, we want to pick the definition of well separated that, is going to work, essentially. That's going to help us, disambiguate these 3 sets of points. So we might say, for instance, maybe the centroids of these 2 clusters are pretty far apart from each other. So we might say that they're well separated. But basically, we might say something like, the average distance between all pairs of points, in this set here and this set here are pretty far apart from each other. So we might say that these are well separated. But, for instance, we can see that these points here are, generally speaking, they are, these points here are pretty far apart from the blue cluster, and they're also far apart from the red cluster. But unfortunately, this notion of a well-separated cluster is going to break down because we actually see that observations here and observations here are even further apart from each other. So implicit in the well-separated definition of a cluster implies that basically all of the observations within the same cluster should be closer to each other than the observations, within another cluster, if you will. So unfortunately, the well-separated cluster definition is not going to necessarily work for us if we're using the Euclidean distance metric. Now, it's entirely possible that we could come up with some other notion of distance between 2 points here that may actually work effectively with the well-separated definition of a cluster. But at face value, Euclidean distance is not going to help us, if you will. Now, what I'm going to explore, so something that we might use here is a graph-based definition of a cluster. So generally speaking, when we're if at least one of our clusters in a data set is non-convex and not well separated from the other clusters, then a graph-based cluster definition can sometimes be effective. So for instance, we might choose to say, we might say that two observations are connected if they are within, let's see, so how far apart are these 2 points here? So basically, if they are within 0.3 units distance of each other, and we might say two observations are similar if they can join in a connected path, or a path of connected points. Okay, so we can see here, for instance, that all of these green points here are connected, all of these points here are connected, and so therefore this point and this point can join in a connected path, so they're considered similar. And same thing goes for these points here. So basically we can connect all of the red points to each other in a connected path, so they're all similar. We can connect all of the blue points in a connected path, so they're all similar to each other. However, for instance, there's no two red or green points that are within 0.3 distance of each other. So therefore, the red points and the green points will never connect to each other, so they are dissimilar. And similarly, there's no two red or blue points that are within 0.3 of each other. So the blue and the red points are not considered similar to each other. And same thing for the green and the blue points. So therefore, a graph-based cluster definition can, in fact, be used to help us find three clusters, which are all considered similar to each other, and all also are considered dissimilar, or excuse me, three clusters in which the observations within the cluster are all similar to each other, and the observations between the clusters are all considered dissimilar to each other. Okay. All right, so any questions on that? All right, cool. So as you can see, we're moving on to Unit 3, which is going to be not talking about any new clustering algorithms in and of themselves, but it's going to be talking about 5 separate ways in which we might go about evaluating a particular clustering algorithm's performance. Or in addition, basically asking questions or asking questions about the results of a given clustering algorithm, basically. So there's going to be 3 questions, or excuse me, what did I say? 3, 5 types of questions that we might ask about a given data set itself, or perhaps the result of a given clustering algorithm performed on a given data set. So again, we're going to ask one of the questions that we've explored in previous units, which is first to determine if a data set is clusterable or not. So we've talked about some ways of measuring that, so by using the elbow plot method, but we're going to talk about some of the downsides of simply just using the elbow plot method to ask that question. Now next, we want to remember that cluster analysis should be used for unsupervised learning purposes. So what that means is we don't ever want to assume that we have a set of class labels in which our goal is to predict them. So the data set that we're going to be exploring in this unit is going to be comprised of 5 numerical variables, these here, and it's also going to contain this additional categorical variable. So basically what our goal is for this analysis is to take these 5 numerical variables and cluster them. And then we have this additional, what we're going to call it pre-assigned class or set of class labels, in which we're not going to cluster. We're not going to include that categorical variable in our clustering algorithms. One, because we want to remember none of the clustering algorithms that we've talked about so far are designed to incorporate categorical variables. But we're going to incorporate this set of class labels to ask a question at the end of the analysis. So in other words, we're going to take this set of numerical variables and we're going to cluster it into however many clusters we deem appropriate using k-means. And say for instance, we identified this as a cluster, this is a cluster, and this is a cluster from our 5 numerical variables. And so we're going to ask ourselves not the question of how well did our clustering algorithm predict the class labels. So that's not our goal. That would be a supervised learning analysis. But instead, we're simply just going to ask a question of association. So we're going to ask the question, is there an association between the clustering algorithm results and a set of pre-assigned class labels? Okay, now basically what this data set is it's a series of metrics for a set of eBay auctions. So it kind of details various pieces of information that you could measure about a given eBay auction. And the set of class labels that we're going to be exploring is essentially whether or not this behavior known as shill bidding was engaged in that given eBay auction. So basically, a normal auction, if you will, simply just implies that there was no shill bidding involved. However, if the class label says abnormal, it's highly suspected that shill bidding was happening in that auction, which is sort of on the borderline between illegal and legal. So essentially, shill bidding is when you, for instance, like get your friends to like help to bid on a particular product that you're posting on eBay in order to artificially jack up the price. So it's not the most ethical behavior. So basically, if you're designing a supervised learning algorithm, generally speaking, your goal would be to use these 5 numerical variables to predict this response variable. But often, before performing a predictive analysis, it's often a good idea to describe the nature of the data set as best as you can, to extract hidden insights, if you will. So again, our goal is not going to be to predict these class labels, but we're simply just going to explore how do these clusters that we find, if we find any, how do they associate with the class labels? Okay, so again, I emphasize this because I see this misconception a lot. Your goal of a cluster analysis is never to predict the class labels. It's simply just to measure, or for instance, it could be to measure the association between a set of class labels. And then oftentimes in a cluster analysis, you're not even given a set of class labels. They're sort of this superfluous add-on that you might have. So we're going to ask other questions. For instance, how do we actually evaluate if a clustering algorithm effectively clustered our data set? So that's going to get us thinking about, how do we know that a given clustering result is good or bad? So we're going to be thinking about what we call unsupervised clustering evaluation metrics. All right, so we'll get to all these 5 questions that we're going to ask as we move on through the unit. But the first question that we wanted to ask, like we mentioned, is how do we go about evaluating if a data set is clusterable or not? Or in other words, should we even be performing a cluster analysis? So to define a clusterable data set a little bit more succinctly, we simply describe a data set as clusterable if there exists some distinct grouping in the data. Okay, so again, I'm giving you another vague definition. So how might this definition be considered vague? Yeah, so what do we mean? We might ask ourselves, what do we mean by distinct? Yeah. And so there's a wide variety of ways in which you could answer that question. So much in the same way that there's a myriad of different clustering algorithms that exist, because we can define a cluster in a myriad of different ways, there's a myriad of different evaluation metrics which even just simply answer or evaluate the question of, is the data set clusterable? So we might have different notions of what a clusterable data set is based on what we mean by distinct. So that's what we're going to talk about here in this unit. What are some ways that we might go about evaluating or answering that question, specifically for a set of numerical variables? And we also want to think about, why is this question important? Let's just say, for instance, we have this data set that is, again, basically just a blob of points, and we apply k-means to that data set. Let's just say we cluster it into 2 clusters, and we simply just return that data set to, let's just say, our client, and we say, here's the set of observations that belong to cluster 1, and here's the set of observations that belong to cluster 2. And if we're simply just saying that and basically providing no additional information, no additional exploration, then in essence, we could be misleading ourselves as well as misleading the client. So this can be misleading. You may return a set of cluster labels for a given data set with the hidden implication that there is a strong separation between the points in the 2 clusters, when this may actually not be the case. Okay. So before performing cluster analysis, it's always a good idea to assess whether the data set is clusterable in the first place. So we've discussed actually a variety of ways in which we can evaluate if a data set is clusterable. So for starters, we could make or use the k-means elbow plot method to answer that question. So we say that when determining if a clustering structure is specifically detectable by k-means, we can use a k-means elbow plot that plots the inertia of clusterings found by k-means with k equals 1, k equals 2, 3 clusters respectively. And again, if we see an elbow, a strong elbow or any kind of elbow in that plot, what that implies is that k-means is identifying, at the very least, this many clusters. Okay? And so you want to remember what we're plotting on the y-axis is the objective function that we were trying to ultimately minimize in the k-means optimization problem. Now that's a k-means elbow plot. So similarly, if we knew that we wanted to use k-metoids to cluster this data set, then we might also make a k-metoids elbow plot. So what we say is when determining if a clustering structure is detectable, in this case by k-metoids, we can use a k-metoids elbow plot. And what this plots is actually not the inertia of a given clustering, but rather what it plots is the objective function that we're trying to ultimately minimize in the k-metoids optimization problem. In other words, the sum of each of the distances of each observation to its centroid, which is the metoid in this case. And so again, much like in k-means elbow plot method, if you see an elbow in this plot, what that represents is, or what that k-value represents, is the number of clusters that k-metoids is able to detect. we're starting to see a pattern here. So in general, many of my clustering algorithms that I'm going to introduce in this class are actually founded upon some sort of optimization problem in which there's some sort of objective function that we are trying to minimize, if you will. So for any type of clustering algorithm that is linked to some sort of optimization problem in which you're trying to minimize this objective function, whatever it is, then you can create a elbow plot that corresponds to this particular algorithm. So we say when determining if a clustering structure is, detectable by the particular clustering algorithm we're using, can use an elbow plot that plots the objective function of the clusterings found by this particular algorithm. And we can go about interpreting it in a very similar way. So what we put on the y-axis is the objective function value of the corresponding clusterings that we create. And if we see an elbow, then that means that that particular algorithm is detecting a clustering structure at that elbow point, so at that k value. Oh. Yep. Detecting this many clusters. Okay. So perhaps we're seeing some drawbacks to the elbow plot method for determining if a data set is clusterable. So what are some drawbacks that we're essentially seeing here? You can put it in the chat. You can raise your hand, tell me what it is, or you can shout it out. So I did see that in the Getting to Know You survey, there were, I think, a pretty good amount of people that wanted to raise their hands and answer questions in class. It's not too many and it's not too little. So I would say if you were one of those people that wanted to raise your hands, I'd say definitely go for it. So I'm seeing two direct messages here. It's hard to quantify. It's very visual. There's no standardized test in place to test the validity of an elbow plot method. So these are all good points as well. So it is more of a qualitative assessment. But what I would want to focus on is that each of these evaluation metrics that we've discussed is algorithm dependent, right? Each method is only able to detect clusters that one particular algorithm is designed to detect. So we might, for instance, not even be at the phase of determining which clustering algorithm that we're looking for. We might simply just want to ask, is this cluster or is this data set clusterable at all, regardless of the clustering algorithm that we're using? So it's possible, for instance, that we might have a data set like this, that k-means is not designed to detect the clustering structure of, and in addition, k-metoids is also not designed to detect the clustering structure of. And so basically, by simply just bounding ourselves to using a given clustering algorithm to detect the clustering structure, it's possible that, we may actually not know the best clustering algorithm yet to detect this structure. So we'd like to identify an evaluation metric which is independent of one particular clustering algorithm that can, in fact, identify whether a clustering or whether a data set is clusterable just in general, regardless of the algorithm that we're using. So here's one such algorithm independent method that we use that attempts to detect whether a clustering or whether a data set is clusterable in general. However, what we're going to see here in this class is there's no method or no algorithm that is a silver bullet. Or in other words, it's going to be effective for every possible data set that we might think of. Because again, just like what we're seeing with clustering algorithms, there's many different ways in which we might define if a data set is clusterable. So each of these definitions are going to be built upon their own particular assumption as to what it means for a data set to be, in fact, clusterable. So the Hopkins statistic, it does measure, it's one such measure of the clusterability of a data set. And a potential nice thing is that it is not algorithm dependent. And so basically, here's the assumption that we end up using for the Hopkins statistic. We say that a numerical data set is clusterable if there are a lot of large gaps that exist within the range of points of the data set. Okay. So for instance, we've more or less put a range around the X, or we've kind of focused the window of X-axis and Y-axis points around this data set here. And so for instance, we do see a lot of gaps that exist within this range of points. So our Hopkins statistic assumption might in fact say that this is in fact a clusterable data set, which we can see that it is. So for instance, let's start, let's come back to this question, but immediately when I introduce any type of metric and the assumption that that metric is based upon, I want you guys to start trying to troubleshoot this. So try to break this metric. So as we're going through how this, Hopkins statistic is actually calculated, try to think about ways in which this assumption might break down. So try to think about clusterable data sets that this assumption would not be able to detect as clusterable. And then also try to think about unclusterable data sets in which this metric would actually say that the data set is clusterable. So kind of keep that in your back mind. But let's go into how this Hopkins statistic is actually calculated first. So the input in this, so basically again, this only really considers numerical variables. So it's basically just a numerical data set with n attributes. And so here's what you're going to do. You're going to randomly create or select two sets of points. I was using a color scheme here. Okay. So the first set of points are going to be a random or a set of randomly generated artificial data points within the range of values of the data set. So you're going to randomly select P observations within the range of points. So I might get some here. And for this data set here, I can see that there's a lot of gaps. So it does look like a lot of these artificially generated points would end up in the gaps as opposed to the clusters. And so then what we're going to do with each of these points that we have randomly generated is we are going to find the distance of each of those points to their nearest neighbor in the data set. Okay. So you get a set of U distances. All right, so we're just going to keep that and move on to the second set of observations that we're going to now randomly select. So next what we're going to do is we're going to randomly select P actual points in the data set. And then what we're going to do is we're going to find the distance of each of these points to their nearest neighbor. So that creates these WI distances. Okay, so putting it all together, my Hopkins statistic is going to be the ratio of my actual point, nearest neighbor's distances, divided by my actual point, nearest neighbor distances, plus my randomly generated artificial point, nearest neighbor distances. Okay? And so I want you to think about how this Hopkins statistic is generated to give us a sense as to what types of Hopkins statistic values suggest a clusterable data set and what types of Hopkins statistic values suggest a less clusterable data set. So what I'm going to do is I'm going to open up some breakout rooms, and I want you guys to discuss or roughly approximate what you think the Hopkins statistic would be for data set 1 and what the Hopkins statistic would be for data set 2. So basically what I've done for you here is I have these orange points are randomly generated artificial points, which were randomly generated or randomly selected in the range of values of this data set. And then the green points are randomly selected data points for each of these two data sets here, which can kind of give you a visual aid. So what I would suggest is taking a screen cap of this image here if you need it. It's also in the notes. And yeah, I'm going to open up the rooms. You can select your own room. I would say pick a room with about 4 people. Discuss what you think the answer is, and then we'll meet back and discuss. Okay. All right. So in the interest of time, I'm just going to start assigning people to random rooms, but you can always change it if you'd like. And if I end up seeing a huge room with like 20 people in it, I might start booting some people. So try to stick to smaller rooms. Okay, so it looks like everybody is now assigned to a room. So if you can go there now, we will meet back and discuss in a few minutes. Oh, shoot. All right, so I just closed the breakout room, so I'll give everybody a few seconds to make it back. While you guys were in the breakout rooms, I realized that I made a mistake. I mentioned that today was going to be our first checking Tuesday, and I did not actually set it up. So I'll send out an email and I'll wait till everybody gets back here. But yeah, bullet point is there's actually going to be no checking Tuesday today. Um, I'll state that again once everybody is back. Oh wait, I haven't actually closed the rooms yet. Hold on. All right. Okay. So now we've just closed the rooms. So everybody should be back here very soon. Okay, so I think we've hit a critical mass. Okay, so I wanted to make a point here in just a second, but I wanted to wait till everybody gets back from the breakout rooms. Bullet point is, as you guys were in the breakout rooms, I realized that I completely forgot to set up the checking Tuesday for today. So good news, there's no checking Tuesday for today. Everybody will have the chance to be checked eventually, but bullet point is it's actually not going to happen today. So sorry about that. All right, but back to the question at hand. Let's take a look at data set one. So what would we approximate the Hopkins statistic for data set one to be? Close. Yeah. So we can see this data set here, we can visually see with our eyes is not clusterable. There's no distinct groupings of points. And so, yeah, we can see basically that the sum of the actual point distances, the WIs, because of that, is going to look very close to the sum of the artificial point distances. So basically, what that means is that these two values here are very close to each other. So therefore, this value ends up being approximately equal to 1/2. So yeah, generally speaking, that is how we would interpret Hopkins statistics that approach 0.5 from the left. So we see that if a Hopkins statistic is close to 0.5, this suggests that the data set is less clusterable. On the other hand, we have data set 2, which we can see with our eyes is in fact very clusterable. And because of these gaps that exist, or the artificial point, or basically because of these gaps that exist within the window of points in the range, or basically the range around the window of points, our artificial point nearest neighbors distances are going to be comparatively a lot larger than the actual point distances to their nearest neighbor. So because of that, this ratio, the denominator of this ratio is going to be comparatively a lot larger, and therefore our Hopkins statistic is going to approach 0. So generally speaking, if the Hopkins statistic is close to 0, then this suggests that the data set is more clusterable. Okay. All right, cool. So any questions on that? All right. And so there's a couple of parameters, well, actually one parameter that was introduced when it came to calculating this Hopkins statistic. So the parameter that we would want to think about is, well, okay, how many random points do we want to select in the data set, and how many random artificial points do we want to select within the range of data set values? So a good rule of thumb that the researchers have found tends to work pretty effectively is to set your p-value, i.e. your value of p, to be about 10% of the observations in the data set. Okay. Now, in addition to a algorithm being non-deterministic or deterministic based on the way that it's designed, our clustering evaluation metrics can also be deterministic or non-deterministic. So what would we say? Is the Hopkins statistic a deterministic or non-deterministic evaluation metric? Yeah, it is in fact non-deterministic because it has a random element to how the metric is calculated. So again, we are randomly selecting a set of P artificial points and a set of P actual data points. So therefore, your Hopkins statistic, unless you fix a random seed, is going to be different every time you calculate it. So therefore, you would want to think about how you might go about extracting the most amount of meaningful insights from this Hopkins statistic. So one such thing that you can do is, for instance, calculate many Hopkins statistics and perhaps evaluate the average and the standard deviation of each of these statistics to get a more clear sense as to whether your data set is clusterable or not. Okay. All right, any questions on that? All right, so I wanted you guys to be thinking of some ways that we could break this evaluation metric. So let's go back to these questions here. So can you think of a clusterable data set that would most likely not be detected under the Hopkins statistic assumption of clusterability? Let me draw my range. Let's just say this is my range of values, my X and my Y. Any ideas? Dense clusters with sparse data points surrounding the dense clusters. Yeah, so let's see here. So we had so a density-based notion of clusters. Yeah, so having a density-based notion of clusters would make the Hopkins statistic less effective. I'll say that. But yeah, we still are seeing, these inherent gaps here. So like if this was our particular data set here. So even if we have some noise around our clusters, regardless, when we pick our artificial points, those artificial points are still going to be, on average, a lot further away from their closest point than the actual data points that we select. Now, this is kind of a question as to like, well, how much noise do you actually have in your data set? So if you only have like a few noise points, then it's highly unlikely that when we randomly select actual points, that they're going to be those noise points. And so therefore, when we select the actual points, their nearest neighbors distances are going to be, comparatively smaller. But yeah, if we do have more noise points, then it becomes more likely that the random points that we select will in fact be the noise points. And therefore their nearest neighbors distances are going to be further away, therefore, contributing to a much more similar ratio between the nearest neighbor points of the actual points versus the artificial points, therefore making the Hopkins statistic closer to 0.5 and making it look less clusterable. But yeah, basically a noisy data set, it definitely weakens the strength of the clustering structure. But let's just say, what if we had two clusters like this? I'm trying to draw this effectively here, that were basically just stacked on top of each other. And let's also say that they were, not the most well separated, but they definitely were still clusterable, if you will. I need to turn this off. So we have, these two distinct clusters here, like this. And they're not well separated, but definitely distinct enough. But their placement, basically stacked right on top of each other, unfortunately does not leave a whole lot of gaps for the Hopkins statistic to essentially detect. So for instance, two stacked clusters don't leave a lot of gaps. For the Hopkins statistic to detect, and therefore it might suggest that the data set is less clusterable than it is. Okay. And then furthermore, let's think of an opposite or scenario in which, for instance, we have a data set which is more or less like a blob of points. And maybe we have an outlier here. So now here's going to be my range of values that I'm going to be randomly selecting artificial data points from. So in this case, our range of values actually leaves a lot of gaps. So now, and again, you'd want to think about, do you actually consider this to be a clusterable data set or not? Do you consider this outlier to be a cluster? And do you consider basically every other point to be its own cluster? If the answer is no, then unfortunately the Hopkins statistic is going to fail in this case. So basically, if you consider the data set below to be unclusterable, then the Hopkins statistic will detect a lot of gaps, and it will suggest a Hopkins statistic value that is closer to 0, suggesting that this unclusterable data set is in fact clusterable. Okay, so that's how the Hopkins statistic metric breaks down in the other direction, in which you have an unclusterable data set, but the Hopkins statistic suggests that it is clusterable. Okay, so therefore, given that each of these evaluation metrics that we're using, each of these algorithms that we're using are based on their own separate assumptions, it's usually a good idea in order to be the most informed about what's going on in your data set, it's usually a good idea to apply an arsenal of different tools to the same data set. So an arsenal of different algorithms, different evaluation metrics. So you can be as informed as you can about what's actually going on in your data set. All right. Questions on that? All right, cool. So another really cool clusterability evaluation technique that we're going to discuss in the next unit is what's known as TSNE plots. And this is actually one of my favorite unsupervised learning algorithms. So we'll get to that in the next unit, but yeah, we will discuss this question more thoroughly. I'll just say that. So let's move on to another question that we might ask of a data set, which we intend to use for cluster analysis. So let's just say, for instance, we've decided that our data set is in fact clusterable. So we'd like to, cluster it, if you will. So then the next question is, let's just say we've applied a given clustering algorithm to the data set. So then the next question is, how might we evaluate whether the clustering algorithm provided an effective, performance, if you will, on that particular data set? So questions such as this, basically, how did your clustering algorithm perform, get to, or basically best described as unsupervised clustering evaluation metrics. So there's no set of, additional class labels that we're bringing in after the analysis. We're simply just taking the data set, taking the clustering that we found, and asking ourselves, how well did the clustering algorithm perform when it came to clustering the data set? So we say that unsupervised clustering evaluation metrics evaluate the goodness of the clustering without using any pre-assigned class labels. So when evaluating how well a given clustering algorithm did, it's fruitful to think about, well, what is our overall general goal of a clustering algorithm? Well, we said it's simply to find a grouping of observations, clusters, such that the similarity of the objects within the same cluster is maximized, while this similarity of objects in different clusters is minimized. So we want to come up with a general definition for how we might, basically describe this intra-group similarity and this inter-group similarity. So we define the cohesion of a given cluster as measuring how closely related or how similar the objects in a given cluster are. And we define separation as measuring how distinct or well separated the observations in two clusters are from each other. And to combine both of these terms to basically measure the overall cohesion and separation of the entire clustering, we define what we call validity, which can be expressed as some function of the cohesion and separation of all of the clusterings in a given clustering of a data set. Okay, so I have given you another vague definition. So what are some vague elements of this definition? Yeah, what is this function? Yeah, we might ask that. What is this function that combines cohesion and separation? It's one thing that we can ask. Anything else? Yeah, exactly. What does it mean to be two clusters to be well separated? Yeah. We might also ask the question, I'm seeing this in a direct message. What does it mean for clusters or observations in a cluster to be considered similar? Okay. So much like there are many different types of clustering algorithms, there are many different types of unsupervised clustering evaluation metrics, which, answer these questions in a variety of different ways. So much in the same way that we have a graph-based definition of a cluster, we also have a graph-based view of cohesion and separation of a given clustering. So when calculating a graph-based notion of cohesion and separation of clusters, ultimately what is involved first is creating a proximity graph of all observations in the data set. And so basically we measure this proximity, or the proximity between each pairs of observations in this data set. So how is this definition vague? Any ideas? Yeah, exactly. So we might ask ourselves, how do we measure proximity? Okay. So this notion of proximity, we want to be, there's two ways in which we might measure proximity, or two main ways that we can split up this notion of proximity. So we have similarity metric measures of proximity, which basically have this assumption, which says the more similar two objects are, the smaller this proximity measure is. So what would be an example of a similarity metric or defining proximity? So in other words, the smaller this metric is between 2 points, the more similar those 2 points are. Yep, exactly. So basic one, first thing that jumps out is, yeah, simply just Euclidean distance. So the smaller that Euclidean distance is between 2 points, it's implied the more similar those points are. On the other hand, a dissimilarity metric measure of proximity works the opposite way. So we say that the more similar two objects are, the larger this proximity measure might be or is. So what are some examples of a dissimilarity metric measure of proximity? So in other words, the larger that metric is between 2 points, the more similar those points are considered to be. So not Euclidean again. So basically, if the distance between 2 points is large, that generally means those 2 points are very dissimilar or very dissimilar to each other. Yeah. So let's take a look at this data set here. The number of, yeah, exactly. The number of common neighbors, the cosine similarity. Yeah, both of these count. So for instance, the number of common k nearest neighbors, right? So if 2 points, are pretty close to each other, chances are they also share a lot of common neighbors. So the more common neighbors, the more similar you are. So that number increases. And similarly, let's do the cosine, absolute value of the cosine similarity of 2 points. So generally speaking, that value, the closer it is to 1, the more similar those 2 points are. The closer that value is to 0, the more dissimilar those 2 points are. And similarly, like you can actually, come up with many other similarity, or excuse me, dissimilarity metrics for, let's just say, a categorical data set. So for instance, if I wanted to measure the proximity between, let's just say, person 1 and person 2, I might, for instance, count up the number of common attributes that they have. So basically, these two people here have nothing in common. So for categorical data sets, I might say the number of common attributes that two observations share. So for instance, the similarity between observation 1 and 2, that's going to be 0 because they have nothing in common. However, the similarity or the proximity between observation 2 and 3 is going to be 2 because they have 2 attributes in common. So that implies that they are more similar to each other. Okay. So for instance, let's just say we created this proximity matrix here of a given data set with 5 observations. And we also know that we clustered that data set into the following. So 1, 2, and 3 were in cluster 1, and 4 and 5 were in cluster 2. And we said that this clustering was actually a really good clustering. It was pretty good. So based on that knowledge, do we think that we were using a similarity or a dissimilarity metric? So I'll put this into a poll. So 1 is we were using a similarity proximity metric. And 2 is we were using a dissimilarity proximity metric. Let me do a poll. Okay, so given that we said this is a good clustering, what type of proximity metric were we using? Give it a few more seconds. Okay. So majority said 1, it is a similarity proximity metric. But kudos to the 42% that said 2, it is a dissimilarity proximity metric because this is actually the right answer here. So you want to remember, if this is a good clustering, ideally, what that means is we want the observations in this cluster to all be similar to each other. And we want all of the observations in this cluster to be collectively similar to each other. And furthermore, we want the proximity, or the proximity between these two clusters to be relatively dissimilar to each other. So basically, because these are all relatively higher numbers, what that means is that higher numbers or higher proximity values imply more similarity. Lower proximity values imply less similarity. Okay, so given that high values mean more similarity, this implies that this is a good, cluster one is good. There's a lot of similarity within the cluster. Same thing here. And given that low values imply high dissimilarity, this is also good. Basically, that means cluster one and cluster two are very dissimilar from each other. Okay. Questions on that? Okay. Oh, yeah, I did mention there's no checking Tuesday because I forgot to set it up. Sorry about that. So everybody will have the chance to eventually be checked, but yeah, totally slipped my mind. So yeah, we're not going to have it today, but we will have it next Tuesday. So yeah, so one way that we might go about measuring the cohesion of a graph-based cluster, for instance, is by simply just taking the sum of all proximities between all pairs of points. Okay. Excuse me, in that cluster. I know you guys are all very excited about the Checking Tuesday. The nice thing about the Checking Tuesday is I do plan to actually give you guys feedback. So if you, if we identify any misconceptions, in your videos, we will let you know that, we have identified some misconceptions and, we'll kind of clear up what those misconceptions are. But, again, the Checking Wednesday is not about being right. So you're not going to be penalized if you get the right answer. I view this as an effective way to get, more detailed feedback for you guys. So it's not, it's not that big of a deal. Okay. So if we're using this particular cohesion, graph-based notion of cohesion, ideally, if we're dealing with a similarity metric measure of proximity, what this means is that ideally, the overall cohesion value would be relatively small. On the other hand, if we're using a dissimilarity metric measure of proximity, what that means is that ideally the cohesion of a given cluster overall would be large. So that makes sense, right? Because if we're using Euclidean distance, if this, was a good clustering of this data set here, then yeah, we would want all of the pairwise distances of all of the points within this cluster to be relatively small. And similarly, if we're using our dissimilarity metric or measure of proximity here, we would want the sum of all of our proximity measures within a given cluster to be high, essentially. Okay. And similarly, one way that we might go about defining separation in a graph-based cluster, or using this graph-based notion of cohesion and separation, is one in which we're defining separation as the sum of the proximities between all pairs of points in the two clusters that we're considering. Okay. And so similarly, if we are using a similarity metric measure of proximity, like the Euclidean distance, then ideally, the sum of all of the proximities between two clusters, so the sum of all the distances, would be large. And if we're using a dissimilarity metric measure of proximity, for instance, like the cosine similarity magnitude, then ideally we would want the sum of all the intra-cluster proximities like this to be small. Okay. All right, so these are, again, just kind of broad overarching ways that you might go about measuring cohesion and separation using this graph-based notion, which again requires you to calculate some sort of proximity measure between every pair of observations in the data set. Okay, but you want to make sure that you are using an effective measure of proximity based on the actual data set that you are examining. So for instance, we've seen this data set, we've seen these two clusters multiple times. So what do we think would be an ineffective measure of proximity between two objects to assess the cohesion of this clustering? Yeah. Generally speaking, when we see a data set and a set of clusters like this, the Euclidean distance, which is usually our friend, inevitably is going to fail us. So right, if we use the Euclidean distance, then what we can see is, if we were to find the pairwise distances of all of the blue points, then yeah, the sum of all those pairwise distances is going to be, pretty high because this blue cluster is, spread out. And then for instance, if we were to find the pairwise distances of all of the blue points to all of the orange points, the sum of all those intra-cluster distances is actually going to be very comparable to the sum of all the inter-cluster distances of blue and orange, or basically of the blue points. So because of that, because the similarity or the proximity of all of the observations in the blue cluster is comparable to the similarity of all of the observations between clusters, at face value, what that would suggest is that this clustering of these 2 points is not actually a good clustering. But we can see with our eyes that the clustering that we actually found here did in fact find the 2 clusters that we would ideally be looking for. So that tells us Euclidean distance is not going to be an effective proximity measure for actually evaluating that our clustering algorithm did actually do a good job. But as we've seen when exploring this type of data set, there's another proximity measure that we can use, which is based on our definition or our graph-based definition of a cluster. So again, we might use this 2-step definition process to define proximity. So for instance, we might say that 2 observations are connected if they are within a distance of, I don't know, 1 unit of each other. This is more or less going to work. Okay. And we might say 2 observations have a proximity of 1 if they can connect in a path of, or if they can meet in a path of connected 0 otherwise. Okay. So because all of our blue points can meet within that connected path, where connection again is defined by a rough distance of a unit of 1 between each other, what that means is that all of our blue points will have a proximity of 1 with each other. And similarly, all of our orange points will have a proximity measure of 1 with each other because they can all basically connect in a path with each other. But because blue and orange can never connect with each other in a connected path, their proximity is going to be 0. So in this case, essentially what we have just defined here is a dissimilarity proximity metric. And this proximity matrix that we have created using this proximity metric does in fact show us that, or indicate that this is a good clustering, right? So the amount of similarity within the clusters is high. and the amount of dissimilarity, or the amount of similarity between the clusters, is low. So basically, using this proximity measure would indicate that this is a good clustering. Okay. Yeah. So someone's asking, would dbScan work with this data set? And yeah, if you selected your parameters appropriately, dbScan would be able to identify these clusters here. So we're going to talk about dbScan, which is a density-based clustering algorithm, in a few units. But yeah, that is one such example that could identify these two clusters. Okay. All right. Any questions on that? All right. So what we're going to get into in the last 7 minutes of class is a type of common graph-based definition of, or basically a graph-based clustering evaluation metric. And the cool thing about this metric is that it actually measures not just the cohesion and separation of a given cluster, but it actually measures the cohesion and separation of a observation within a cluster. It measures the cohesion and separation of a cluster within a given clustering. And finally, it allows for you to measure the overall cohesion and separation of the entire clustering of a data set. So we'll start at the individual observation level. So we call this metric the silhouette score, the silhouette coefficient. And I realize this is probably a bit of a weird English word. So this is this is how you pronounce that, silhouette. And so the way that we actually calculate, so the silhouette coefficient is actually going to be a combination of both a cohesion metric and a separation metric. So here's how we calculate the silhouette score for a given observation. Let's just call it observation I, which has been assigned to a given cluster and a given clustering. So this involves 3 steps. The first step is to calculate the cohesion metric, which again measures how well assigned this observation is to the cluster it was assigned to. So we calculate this AI value for the given XI object. And so what this measures in words is the average distance XI is from all other points in the cluster it was assigned to. Okay. And then for observation XI, we also calculate a separation metric for it. So this is the BI. And the way that we calculate the BI for a given observation is basically the following. So what we do for each cluster that it was not assigned to, we calculate the average distance XI is from all other points in the cluster it was not assigned to. Okay, so we calculate this average distance for all clusters that it was not assigned to. And then we basically find the minimum distance. Okay. And then finally, we calculate our silhouette coefficient by using that BI and that AI that we just calculated. So this is our SI. And so our silhouette score for a given point is the distance, basically BI minus AI. And then we normalize by the maximum of AI and BI. And this is for basically any cluster that has more than one observation. If a cluster simply just has one observation, then the silhouette score is set to 0. Okay. So I had a little exercise that I wanted to do. Do I have time for this? So I think yeah, on Thursday, we'll go through an exercise where I want you guys to basically approximate what the silhouette score would be for each of these 3 points that I've circled here. So basically use use the definition of the silhouette score to approximate it. But something that we can think about is, for instance, what is the range of values that this silhouette score takes on? So the silhouette score can range between -1 and 1. Okay. And so to interpret what these values mean, I think what I'd like to do is the exercise first. So we'll circle back to that. And then we also want to think about, how is this definition vague? So some blanks that we might choose to fill in when it comes to calculating the silhouette score, for instance, is, yeah, what distance metric would we like to use? Okay. So based on the type of data set, again, the Euclidean distance metric may be more or less useful when using the silhouette coefficient to measure cohesion and separation. So we'll discuss that on Thursday. And then I'll just kind of quickly get to how we might use the silhouette score of a given observation to, for instance, measure the cohesion and separation of a cluster. So for instance, what we do to measure, or a useful plot that we end up using once we have calculated the silhouette score for every observation in the data set, is creating what we call a silhouette plot. So basically, a silhouette plot is basically just a bar plot in which basically we take every observation in the data set and plot a bar for its corresponding silhouette score. So this, in theory, is what your silhouette plot would look like for a given data set. So let's just say you had a data set and you clustered it into 2 clusters. So this is cluster 0 and this is cluster 1. So basically, the additional thing, the silhouette plot is not just a bar plot. You do a little bit of rearranging of the silhouette scores of a given point. So this is cluster 0, this is cluster 1. So another element of a silhouette plot is you arrange each of the observations. Basically, you group them by the cluster that they were assigned to. So this is all the observations, for the silhouette score of all the observations assigned to cluster 1. This is the silhouette score of all the observations assigned to cluster 0. And furthermore, you arrange them in descending order. So these are my highest silhouette scores of observations assigned to cluster 1, all the way down to the lowest values. Okay, so I would say, yeah, between Tuesday and Thursday, think about what these silhouette scores might be, because it's going to give us a sense as to how we actually go about interpreting that silhouette score. So we want to think about, what does it mean if a silhouette score for a given point is 1? What does it mean if a silhouette score for a given point is 0? And what does it mean if a silhouette score for a given point is -1? Okay, so I've gone over. And so I see a question here in the chat. I'll answer that in just a second. But yeah, I'll wrap there. I'm going to stop recording.